Good afternoon, ladies and gentlemen. My name is Katerina Dzimourta. I'm a postdoctoral researcher in the University of Western Macedonia in Greece. And this presentation, I'm an IT engineer by education, so this presentation is more a technical presentation regarding computational systems and the very, to my opinion, interesting field that combines EEG data analysis and artificial intelligence and machine learning methods for brain conditions. So the motivation of this work was my beloved deceased niece, Christina Zoe, who diagnosed with Kleefstra syndrome back in 2013. Christina suffered from seizures, and passed away in 2016 from complications from a major respiratory infection. This presentation and my whole research journey is dedicated to her. To begin with, and sorry to bring this up, but I believe that this was the motivation to start all this work and to exploring the brain and how the brain communicates, and to explore that this is the most complex organ of our system and it's responsible for processing and coordinating various functions. It consists of billions of neurons that we earlier talked about that communicate with each other through electrical signals. So the electroencephalogram, or shortly the EEG, is the non-invasive way that we can capture this communication between the neurons. Various techniques and algorithms have been proposed that combines machine learning methods and EEG data analysis, and in short, we will talk about why. The electroencephalogram is the main diagnostic tool of epilepsy, but while it is the main diagnostic tool, several brain disorders use the EEG to assess the severity, such as Alzheimer's disease or other dementia types, sleep disorders, neurological and developmental disorders, and many other conditions, brain conditions. During the recording of EEG, the following waveforms are shown. Alpha waves that are prominent during relaxed wakefulness with eyes closed, beta waves that are prominent during relaxed wakefulness but with eyes opened, and they are associated also with anxiety or hyperactivity. Gamma waves that are the fastest waveforms that are shown during REM sleep or during full wakefulness, are associated with perception and with high attention. And delta and theta waves that are slow waves. Delta is shown in the electroencephalogram during sleep, during deep sleep, and theta during light sleep or meditation, and they're also associated with pathological findings such as encephalopathies or different brain conditions in neurodegenerative diseases or in epilepsy. Now, some common abnormal EEG recordings, EEG patterns, abnormal EEG patterns associated with epilepsy are shown in this slide. We have spikes and sharp waves that are small, brief, high amplitude, irregular waveforms that are indicative of epileptic activity. The spike wave complex, or the polyspike wave complex, which is actually spikes that are followed by waves. And in this slide, you can see this polyspike wave complex, which is a recording of an absent seizures. And the slow wave activity, which is actually abnormally increased slow wave activity, such as generalized slowing or focal slowing, which is also indicative of encephalopathies or brain injuries or neurodegenerative disorders. Now, in this slide, you can see the EEG recording that is actually 3 or 4 seconds. Imagine being a neurologist and you have to observe, you have to manually inspect an EEG and an electroencephalogram of 24 hours. And imagine that we, from our side, from the IT, we aim to develop an automated seizure detection system, a system that learns. So this is where machine learning comes into play. Machine learning is a subfield of artificial intelligence that is actually focuses on the development of algorithms and models that enable computers to learn and make predictions or decisions. Now, we can train algorithms to recognize these abnormal EEG patterns that are indicative of epilepsy, the spikes, spike wave, polyspike wave complexes, and they can learn from huge amounts of data. The machine learning process in brief, presented in the slide. Even before, well, the first step is to get the data, but even before the first step to get the data, I would say that the first step is to clearly define the goal, clearly set the goal, the problem that we want to solve. So we set the goal, we set the problem, we get the data from various sources, not only from EEG. I'm here to talk about EEG, but the problem is the combination. We need to find data from various sources. The second step is to clean, prepare, and manipulate the data. To gather and collect all the relevant data for our problem, to clean this step, it means that we need to remove any noise from the EEG recordings that is actually very sensitive. This tool is a very sensitive tool. So we need to remove any noise, we need to handle missing values, transform the data into specific form, and split the data into a training data set and testing data set that is going to be used later on to train the model and test the model. In this phase, we also select the appropriate model for our data. Common models, common algorithms include neural networks, include support vector machines, random forest, or decision trees, to name just a few. So the next step is to train the model based on the training dataset, to test the model based on the testing dataset, and last but not least, to improve, to tune and refine our model based on the data that we have. If the model's performance is not satisfactory, we make adjustments, we iterate. This process is not a one-way process, but is a repetitive process with new data. If we have new data, we make adjustments, we make all the appropriate, all the necessary steps again. And of course, once satisfied with the model's performance, we integrate this algorithm, we integrate this model into a system, into an application. We deploy it into an application to make decisions or predictions. Now, EEG analysis combined with machine learning techniques have a great potential for studying and understanding various brain disorders and rare diseases. In the slide, we can see just a few fields where EEG analysis and machine learning are shown. There are hundreds, even thousands of studies exploring machine learning techniques applying machine learning techniques in EEG data. And since electroencephalogram is the main diagnostic tool of epilepsy, the vast majority of these studies focus on seizure detection and seizure prediction. So these algorithms, these machine learning algorithms, learn from the EEG patterns, from the abnormal EEG patterns, and the automated seizure detection systems are proposed. The second, another field of study is the neurodegenerative diseases, where the main focus is on Alzheimer's disease and Parkinson's disease, where we can see quantitative EEG biomarkers for cognitive assessment. They assess the severity of the progression of the disease. In sleep disorders, we have different sleep stages, so the machine learning algorithms, along with EEG data analysis, are here to classify the different stages of sleep and even detect sleep disorders such as insomnia or such as narcolepsy, which is usually confused with epilepsy, and other sleep disturbances. Last, in neurodevelopmental disorders, which is another emerging field of research, where we can see studies focusing on autism spectrum disorder or ADHD and ADHD. Here, machine learning models with EEG data analysis focus on the disorder severity assessment, aiming to improve treatment, to perform a more patient-specific, personalized planning. Sorry about the microphone. Now, the EEG part, the EEG analysis, apart from the clinical purposes, is also used in the field of human-computer interaction. In the slide, you can see several wireless, commercially available EEG recording devices. There is an emerging field, the brain-computer interfaces field, which are systems that will enable direct communication between the human brain and an external device, such as a computer or a prosthetic limb, an external device in general, without any movement from the individual. In the slide, you can also see our PhD student, Mr. Cosmas Lavas, who is navigating the wheelchair directly with his thoughts. So a brief insight of how this intelligent EEG-based wheelchair control system works. The rider wears the, well, you cannot see the pointer, but never mind. The rider wears the EEG recording device where the electroencephalogram is recorded. These devices have numerous of sensors or electrodes that are placed in specific areas in the scalp. So the EEG is recorded from the rider, from the individual of the wheelchair, according to some certain guidelines. The rider is asked to imagine left or right hand movement or blink. And these recordings, these signals are recorded, are sent to the PC via Bluetooth. In the PC, we have the machine learning methodology, where the electroencephalogram is pre-processed to remove any noise, any artifacts, and then features are extracted from the pre-processed EEG signals. After that, the mental commands classification takes place. The data are labeled according to the Mendel's task. So if the rider thinks to move his right hand, this would be translated in real time to right movement of the wheelchair. If the rider thinks to move his left hand, this will be translated in real time for left movement. And if the rider blinks, this will stop the wheelchair. So this is the offline training, which means that this is the training of the system that takes place not in real time. In real time, we have the online testing, which means that the rider wears the hat, the EEG recording device, the signals are transmitted to the computer, features are extracted, and those features are given to the pre-trained model that we trained it during the offline phase, and the commands are classified, and these commands are translated into a signal that is going to be used, that is going to be sent to the wheels, and the wheelchair is going to be moved in real time. Now, turning our attention to Kleefstra syndrome, we know by now that Kleefstra syndrome affects brain development and causes intellectual disability. So in this slide, a few symptoms associated with brain activity are presented, but the most important question, the crucial question is, what are those specific EEG patterns associated with Kleefstra syndrome, and how do these correlate with the neurological symptoms of the syndrome? Later in this session, we talked the presentation about neural communication, and that neurons differentiate, communicate in different way, behave in different way in Kleefstra syndrome than in kids without. Do we know, actually, if there are any EEG patterns? I believe we do not know yet, because we do not have actual data, published data. So machine learning can potentially assist individuals with Kleefstra syndrome in various ways. Diagnosis and early detection, potentially we could see EEG data accompanied with other types of data from brain in order to make safe early diagnosis, early detection. Treatment optimization, where machine learning can assist in optimizing potentially the treatment strategies for individuals with Kleefstra syndrome. Behavior monitoring and support, that machine learning can analyze behavioral patterns, sleep disturbances, repetitive behaviors seen in Kleefstra syndrome individuals. Assistive technologies that I have mentioned about wheelchairs, but not only about wheelchairs, specifically designed assistive technologies for Kleefstra syndrome individuals. For example, that goes beyond the EEG, but for example, a speech recognition system that is specifically designed for individuals with the syndrome. But none of this can be done unless we have data. And this is, to my opinion, and I believe to all of us, the most important part, to have the data to establish biorepositories for Kleefstra syndrome and patient registries and health records, and learn all these associations and relationships between the data. In conclusion, EEG-based machine learning research holds tremendous promise and can aid individuals with the syndrome and with other rare diseases by providing insights into specific patterns of brain activity, helping to understand the neurological aspects of the syndrome better, and understanding the underlying mechanism of the syndrome on the side of the brain. So with ongoing research and collaborations, this is why we are here today. I believe that we can make great breakthroughs on the syndrome. All the references of today's presentation. Thank you very much for your attention.
Yes, thank you very much, Katarina. So we are a little out of time, but we have some room in the afternoon to catch up. Are there urgent questions or not so urgent? Also okay. So I think good to mention, and I think Neil will talk about it tomorrow, that we are collecting in a systematic way now EEG measures in the individuals with the syndrome, not per se because they have seizures, but just as a biomarker and gain knowledge about their quality. And it would be great to connect to other clinical teams, exactly for the reason as you mentioned, to combine data sets that will be beneficial for all of us. Ariane?
Yes, thank you for your nice talk.
Yeah,
I was wondering, like, how do you, I totally agree that it's important to collect this EEG data and that it's important to know what is going on in the brains. But do you collect EEG data already, and do you have worldwide collection or only in Greece? And can you tell something about that?
Well, thank you. Thank you very much for the question, because that gives me the opportunity to highlight the problem that we have in Greece. To the best of my knowledge, in Greece, I know 3 families that have an individual, a kid with Kleefstra syndrome. So it's very hard, and the sample is limited, and it's very hard to record signals from Kleefstra syndrome cases. But we have recorded from epileptic patients and from patients with dementia, Alzheimer's disease, and frontotemporal dementia. And a few days ago, we actually published a data set that is openly available under the Open Neuro platform on Alzheimer's disease cases and frontotemporal with EEG recordings from these cases. And our next step is the epileptic cases, where a big problem is that there are not publicly available datasets of many cases. We have datasets of 20 cases, of 5 cases, or even for 30 cases. Okay, but we have machine learning algorithms that can learn from huge amounts of data. And it would be excellent if we had EEG data and blood samples and genetic samples and all the other. Okay, thank you. Thank you for your question.